Stardew Valley is my favourite game to play to unwind, where the days are long, there's lots to discover at your own pace, and hardly anything ever goes wrong. As a data analyst, I believe that data and analytics can be used in every aspect of our lives. In this video, I'm going to show you how I use data to optimize 3 tasks in Stardew Valley, with no cheating and no mods. Finding the fastest way to harvest crops, clustering characters to streamline gift giving, and building analytics to monitor my farm without ever leaving the house. I'm Lily, I love data, I love Stardew Valley. Let's have fun with both for the next 18 minutes. Okay, so I've always suspected that when I'm harvesting crops in Stardew Valley, it's a lot faster to go right than it is to go left. It's never bothered me enough to do anything about it, but I definitely noticed that coming back feels like it takes way longer. And if I'm right, I'm potentially wasting a lot of time. The first thing I wanted to validate was, is it actually faster to harvest going right? And if it is, by how much? I started off by recording myself in both directions, and watching it side by side, you can already tell there's a difference in speed. Going right takes 1 second or 14% less time. So right away this disproved my theory that you could save time harvesting only right, because the walk back takes almost double the amount of time you would save. I needed to go deeper and look at what was happening between each crop. I didn't want to be manually working out the timestamps of each harvest, so I used something called audio segmentation. These are the audio waveforms of both clips. It visualizes a sound wave in terms of its amplitude, or amount of energy, or as we perceive it, loudness, over time in seconds. If we zoom all the way in and look at the number of repetitions of a wave in a period of time, we can also extract the frequency or pitch of a sound. These points are where there are significant changes in both energy and frequency, and it's a way to detect when a new sound starts. Where I'm going with this is I wanted a scientific and computational way of getting the timestamps of each harvest, and this was a solution that saved me a lot of tedious work. Something interesting happened when I plotted the timestamps of harvesting each crop. The time differences between going right versus left got bigger and bigger the more crops you harvested. Maybe it wouldn't make a significant difference if I went left sometimes, but only for a few crops at a time. I also recorded harvesting going up and down and compared those times, and they were pretty similar to going right, just a little bit slower for some crops. Honestly, I could have stopped there and designed a better path by changing directions more often or avoiding going left for long stretches, but I wanted to take this one step further with graph theory. We can conceptualize our problem as a graph where each crop is a node and there's a harvesting path made up of the edges that connect the nodes. And this is a minimum spanning tree problem, where we want a path that touches every node, also known as edge cover, and we want the path to minimize the distance or time traveled. Our graph has a few extra rules. We can start and end at any node. It has to be a continuous path that's walkable in one go. We have different travel times between crops, which act as edge weights. Because the travel times vary based on direction, any given pair of adjacent nodes actually has 2 different edge weights, but we're able to travel in both directions at any time. And lastly, the travel times vary based on how long we've been going in that direction. There are many algorithms designed to solve the minimum spanning tree and shortest path problems, and they fit some of our rules, but not all of them, particularly with the dynamic travel times. So I attempted to write my own algorithm using Python, based loosely on Prim's algorithm, because it can fit most of the rules. Prim's algorithm starts at a random node, stores the edge weights of its unvisited neighbours, and visits the one with the lowest weight. Each node it visits, the node is removed from play so it can't be visited again, and from that node, the neighbouring edge weights are assessed. If a weight to a node is lower than the one stored, the stored weight is updated to the lower one. The next node it visits is the closest reachable node from the nodes that have already been connected. It keeps repeating this until all nodes have been visited, and we end up with all nodes being connected with the minimum total edge weights. There's 2 main reasons why I needed to modify this for my graph. It's based on edge weights that don't change, and it doesn't necessarily create a continuous path that's walkable in one go. Where my algorithm deviates from Prim is that each step, it only considers traveling to nodes that are reachable from the node it's currently visiting. This way it can count how many times it's traveled in a direction in a row and calculate the edge weights dynamically. Like Prim, each node it visits, it can't visit again, and the algorithm keeps going until there are no nodes left. This was great. I thought I was going to hit run and get a bunch of simulations and find that fastest path. I was wrong. My first simulation went like this. It got stuck because all the adjacent nodes had already been removed. I had built a dum-dum. There are many things I could have added to make it a more complete algorithm, like when it gets stuck, take a number of steps back and make the next best decision, or apply a shortest path algorithm at each step to find the fastest next few steps at a time, not just one step, or get it to solve smaller parts of the graph and put it all together. But I told you I was going to take this one step further with graph theory. I wasn't lying when I said one. This is as far as I went. Simply adding in the ability to travel to 2 nodes away if it got stuck gave me plenty of paths to work with. This was the fastest one that touched all nodes. It takes advantage of going right and up, which are the fastest directions. Then when it can't go any further right, it goes up and down traveling left, comes back around and goes right, up and loop-de-doo again. There was something counterintuitive about it, and that was all the times it went left, even though left is the slowest direction. But based on the logic of the algorithm of thinking one step at a time, it was absolutely correct in prioritizing going right and up, and it had to find the fastest way to come back left. What I took from this is that up and down, which are comparable to going right, the fastest direction, is a quick formation, and there's some form of it in most of the algorithm's fastest parts. I played around with the idea of starting here, and going up and down traveling right, completely avoiding going left. It's 1% faster than the algorithm's fastest path. The starting node is closer to the entrance of the greenhouse, and it's a much simpler, more intuitive path to walk in the game. An algorithm with more advanced decision-making logic could probably find a faster path, but I was pretty happy with this because it was theoretically going to cut down harvest time by 8% compared to my old route of going all the way across right and left. Okay, here's where things got complicated. The next step was to test the paths in the game, but the algorithm's fastest path can't actually be done in the game. I've misled you up until this point, but for good reasons. Hear me out. In the game, if you harvest going left or right, you also harvest the row above and below at once. You harvest 3 rows at a time. You can harvest 1 row at a time if you stay at the edge like this, but to do this path, it's not possible to do this part without also harvesting these rows. Okay, so why didn't I just write this into the algorithm to begin with? I wanted to work with a simplified version of this problem to develop the algorithm before adding in that layer of complexity. And I put it in this video because in terms of demonstrating graph theory, it's a lot easier to digest and it's a pretty interesting problem. But there's also a compelling case for harvesting 1 row at a time in the game. And that is, you can harvest and plant the next seed at the same time, which is very efficient, and you can only do this 1 row at a time. Another complication is that these 6 nodes are actually sprinklers, which you can't walk through. It doesn't make this path impossible, but it makes it very, very undesirable. I mean, look at it. It's insanity. And it was pandemonium testing it in the game because it turns out it's really hard to turn corners quickly and cleanly and stick to the path. Okay, you can salvage this. This is okay. How did that happen? I fucked it. It's not okay! In the end, for my sanity, I decided it was okay for the test to be close enough to the path, and I settled for the best of 18 tries. Here's how both paths went. Even with all the fumbles I made, the algorithm's fastest path was 5 seconds or 6% faster than my old path of going right and left. The path inspired by the algorithm, which was much easier to walk in the game, was 10 seconds or 13% faster than my old path. Even better, it was 18 seconds or 21% faster than harvesting 3 rows at a time and then planting seeds. I did build into the algorithm harvesting 3 rows at a time, but its fastest path didn't actually save me any time in practice. But that doesn't really matter because harvesting and planting one row at a time is the most efficient thing to do anyway. The algorithm got me most of the way there, and adding my human intuition and doing some real-life tests produced a much better solution. And if my sloppy work could cut down harvest time by 10 to 20%, imagine what a machine on a real-life farm could do. Anyway, another vital function in Stardew Valley is gift giving. Just like in real life, giving gifts to the village characters helps you build friendships, and your friends will send you gifts and recipes in the mail. Each person has gifts that they like more than others, and favourite gifts that they love. I used to pick a small group of people at random and give them the maximum of 2 gifts a week, and it took me a long time to become friends with everyone. So I thought, if I were to do it again, how can I be more organised with gift giving? Like have people in clear clusters and level up friendships really quickly using the same gifts. And that got me giddier than getting gifts in the mail. The first thing I did was scrape the Stardew Valley wiki to get everyone's favourite gifts, and I visualised this in a graph. Yeah, remember graph theory? We can make a graph of this too, where each person is a node connected by edges to other nodes of their favourite gifts, and there are edges that connect other people to mutual favourite gifts. And this is what we get. The grey nodes are people, and the colourful nodes are mutual gifts, and we can see how they're all connected. Like we can see both Clint and Kent love fiddlehead risotto, Linus, Pam and Sam love cactus fruit, and pretty much everyone loves diamonds. This is really cool to see, but it's cluttered, and it doesn't help separate people into discrete groups, because some people have multiple gifts in common, or have different gifts in common with different people. One technique that's useful for grouping data points into discrete clusters is clustering, and this is what I explored. You can do top-down clustering, like k-means, where you select how many clusters to create, and the algorithm iteratively puts each data point into a cluster, until each cluster's data points are as close as possible to its mean. Or you can do bottom-up clustering, like hierarchical agglomerative clustering, where the algorithm iteratively merges pairs of clusters based on distance, until all clusters are under one single cluster, and you've got a hierarchy of clusters. So far I've been referring to our villages as data points, which is rude, and they're not data points yet. They don't have any features that tell us how similar or dissimilar they are to each other. But we can create features by turning our categorical data on their favourite gifts into numerical data, and we can perform the clustering on this matrix. I tested 3 different clustering algorithms, and they were really good at creating clusters where people had multiple gifts in common, but they weren't able to put everyone else into a clean cluster with a single mutual gift. This is because there are so many unique gift items, and there just aren't enough people with similar combinations of gifts. And people were being put into clusters that they didn't quite fit into, but they didn't quite fit into another cluster. This wasn't the solution for me. I don't necessarily need clusters that tell me what combinations of gifts people have in common, because I only want to know which one gift I can give to them all. I'd be much better off having fewer, larger clusters where the people have at least one gift in common. Hi honey, I got you a diamond.
Oh my gosh, my favorite. How did you know?
You and 7 other people.
What?
Nothing. In the end, the simplest solution was the best one. With my table of people and their favourite gifts, I wrote a Python script to iteratively count the number of times a gift was in the table. And for the largest group, it would put the people in a cluster and remove their other favourite gifts from the table, repeating until there were no people left. In theory, you can end up with different clusters each time you run this, because there are equal highest counts, and prioritising one means those people can't be put into other clusters. But there are only really 2 results that maximise the number of people being put into a clean cluster. Both these results put 24 or 70% of people into clean clusters, and the remaining 10 people can get assigned any one of their favourite gifts. I got my script to prioritise gifts that I have on my farm, information that's easily accessible in the game's save file. And now I have these dynamic clusters that make gift giving way more convenient. I can just go to my shed, put a few things in my backpack, and be on my merry way.
Why do you have so many diamonds in your backpack?
There are certain things I check on my farm every morning. Hello planties, are you ready? Eat up my lovelies! Can I drink my fancy wine yet? Today? Hello? It's all in the fun of playing Stardew Valley. But you know what else is fun? Building sexy analytics. Like, what if all the things I monitor on my farm I can see in one place in a pretty dashboard? Before I make a dashboard, I always prioritize the most meaningful metrics to the use case, because there's only so much you can fit on a page and properly digest. It helps to group them into categories so the final product is easier to read. Then I used a Python library called Beautiful Soup to parse the game's save file and filter to the HTML tags that contained my metrics. Using a Python visualization library, Plotly, I designed a card template to display my metrics. Each metric would have an image, a number indicator, and a title. And before long, I had cards for things like how many diamonds I have, how many years Penny will still love me from daily diamond gifts, when my crops will be ready for harvest, how much hay I have left and when to buy more, how my fancy wine is going, whether I have extra luck today. And here it all is in the final design. I even put in a refresh button, so after a game day ends, I can read the updated save file. The most important part of analytics is validating that all the data and calculations are accurate, so I spent some time playing with the dashboard up. It was fun knowing everything I needed to know before I left the front door, like I was a wizard. I knew exactly what needed to get done that day, and my animals never went hungry again from me forgetting to put hay in the silos. Hey, thanks for making it to the end of this video. While some would say this was frivolous, a lot of these examples also mirror real-world data problems, which is what makes this fun for me. Like how audio segmentation is part of the tech that recommends music that you're more likely to enjoy, or how graph theory is used for designing electrical networks and the maps we all carry on our phones, or how clustering is used to optimize sports teams and gameplay strategies. I've also written some articles on graph theory and the dashboard that I built. Links are below if you want to check them out. If you enjoyed this video, please consider liking and subscribing, and you can do so by clicking on the bubble with my face on it right now.